All right. Hello, everyone who joined after we started talking. So today it's lecture 3 of our ICMU Intro to Bayesian Inference course. So just to remind you where we are, we know kind of the basic mechanics of Bayesian inference. We know how to operate if we have posterior. We know how to get quantiles. We inform credible intervals. We know how to form point estimates, being it mean, mode, or median. We only looked so far at relatively simple problems. I would even argue toy examples. And last time we kind of started thinking about this, why this is so big, and we started thinking about Monte Carlo integration, right? So we noticed that most of Bayesian inference tasks require integrals, whether you're taking posterior expectation, or if you need to look at the full posterior and need the normalizing constant, which is an integral, or if you're computing quantiles, you need to solve integral equations. So integrals are really key to practical implementation of Bayesian inference. As a matter of fact, this is the reason why Bayesian inference was not mainstream from the very beginning, because back in the beginning of 20th century, when mathematical statistics was being developed by Fisher and Pearson and others, the machinery for numerical integration was not there. So the Bayesian inference was kind of late, mostly because of these computational bottlenecks. Okay, so the last time I mentioned that Monte Carlo is nice, and we practiced Monte Carlo a little bit, and you will practice it in the homework, and probably have already practiced it in the homework. But Monte Carlo algorithms do not scale, unfortunately, to high dimensions. Which means that we cannot analyze, Bayesian problems, or, numerically tackle them with straight Monte Carlo. Just simple law of large numbers will not work. And the main reason is because it's really hard to do anything when you have a multivariate distribution. It's really hard to draw samples from multivariate distributions. We know only how to do it from a handful of distributions: multivariate normal, multivariate T distribution, multinomial Dirichlet, and I think I am already running out of the distributions I know how to sample from. So it's really maybe 5, 10 standard distributions. And Bayesian inference leads to non-standard distributions. So what do we do there? It turns out that the key, well, at least one of the ways to do it, is to relax the independence assumption, which may seem counterintuitive because we are going to make things more complicated in a sense. Monte Carlo is based on IID sampling, independent and identically distributed samples, and that's why the law of large numbers works. But this independence can be relaxed, and the easiest way to relax independence is using Markov property or Markov chains. So that's why today we will need to do both. We will need to learn a little bit about Markov chains, kind of the minimally sufficient theory or results that will allow us to understand why MCMC works. And so, actually, hold on a second. I forgot to open the chat. Please, as always, feel free to interrupt me, ask questions. I now see the chat, so that's good. And if for some reason you I have a question, but I'm not sure how to ask this in English, feel free also to ask in Ukrainian. Terminology I may not know, but I will probably guess what you mean. I learned recently that Markov chains are really Markov Lensugi Markova. I think that's the term. So I thought it would be more complicated, but no. Okay, so an infinite sequence of, I'm gonna use discrete random variables. It does work for continuous as well, but it's easier to start with discrete. It's called the Markov chain. If for any non-negative integers, and I list here lots of these little indices, they are just placeholders for some numbers, right? I need to plug in some numbers. So what we're doing in this line right here, it looks complicated, but I'm saying, okay, I want the next step of my Markov chain, n+1, or my process. It may not be Markov. And I want to condition on the full history of the process, right? So I'm basically saying I want to know what happened exactly at every step. Step 0, I was at step I0. Maybe it was state 1 or whatever of the variable. And then x2 up to xn. So I'm conditioning on the full history of the process. But the Markov property says it doesn't really matter the full history, only the last visited state matters. So it's the simplest possible situation where in order to decide where to go next randomly, but with some laws, I need to know only my previous state of the system. So that's called the Markov property, and it was designed really as the simplest way to relax independence. There's nothing simpler than Markov property. I guess you can argue maybe exchangeability. You can have non-independence with exchangeable processes. Maybe they are simpler, but not clear. They're very implicit. Now, if I have notice what happens here. So this is Markov property. If I have the following stronger statement, which I say, actually, it doesn't really matter if I'm at step n right now or step m, the probability of going from I to j is the same, no matter where I am in the chain, right? So I'm starting my Markov chain, this process, I'm kind of randomly going from x0 to x1, from x1 to x2. But if it doesn't really matter at what time step I am, then it's a simpler process which called switch color. Then the Markov chain is called homogeneous Markov chain. Then the Markov chain. And that's nice because that means that I only need to specify what these numbers, which are called finite state transition probabilities, or finite time, sorry, or one-step transition probabilities. And so a homogeneous Markov chain on a finite state space is defined by two objects. One, which we haven't talked about, by its initial distribution. And let's call it new S. So this is my handwriting is horrible. So, but in LaTeX that would be new, not mu, right? So I just to make it clear. And so, and this initial distribution is just a vector of probabilities which tell me where to start the process. So maybe all of these probabilities, if I have, let's say, 5 states in my Markov chain, and I can only go from 1 to 2 or to 4 and so on. So then these will be 5 numbers, 5 probabilities that sum to 1. Maybe they're uniform. So it's 1/5 for all 5 states. Each number is 1/5. That's fine. Or you can have a point mass at one of the states and say, I always want to start from state 2. That probability will be 1. The rest will be 0. That's also allowed. And then the second object is transition probability matrix. Matrix P with elements Pij, and where again we will write down very explicitly again. So this new I is probability of x0 being I, and Pij is the transition probability x1 is equal j given x0 is equal I. And notice it doesn't really matter that I'm saying here 0 and I could say probability of x5 is equal j given x4 is equal I. They're all equal, so it doesn't really matter. As long as there's difference between these steps is 1, that's fine. right? Okay. So let's look at the example. So there's a lot of words here. So let me see if I can. I didn't want to write it out, so I wrote it out in advance. But uh, let me see. I'll let you read it with me. So we have a rectangular box, and I'll have a picture in a second. Unfortunately, it doesn't fit on the same screen with the text. Um, yeah, we have a box with a divider in the middle. We have these gas molecules floating around, and the gas molecules can go from one side of the box to another, only one at a time, because this gap in this divider is very small. And the way we are going to evolve the system is that at each time step, we're going to grab the box. And when I'm grabbing the box uniformly at random, I'm actually not seeing the divider. So I'm kind of closing my eyes and I don't know where the divider is. And I just grabbing the one of the gas molecules and I'm putting it on the other side of the box. So let me maybe see. So this is the box. So in this example, we have three gas molecules on the left, four gas molecules on the right, and there's this gap, seven molecules in the system. The system is closed, so the number of molecules cannot go up or down. If it's seven, it's going to remain seven forever. If it's 100, it's going to remain 100 forever. But the number of molecules in the left and on the right will be random, right? And so this is a Markov chain by construction because I don't really need to know where the distribution of these gas molecules were before, because I'm grabbing them uniformly at random. So it matters only configuration at current state matters in terms of me determining the next state probabilistically. How do you feel about this construction? This is the simplest model of diffusion developed, I forgot when, very early by this a couple of Ehrenfest and Ferrises, Ehrenfest and Ehrenfest. They were husband and wife, and they developed this model. Um, I'm blanking right now, probably beginning of 20th century sometime. Um, any questions on this? Did you have time to kind of think about it, the construction? So we're grabbing the box. So for example, I can grab the box, maybe I randomly grab this molecule and I'm gonna move it to the other side. So there will be four on the left and three on the right in the next configuration and so on. And then we'll continue playing this game forever. Okay, what's the state space? How many? So if we define by xn, right? So our Markov chain keeps track of the number of molecules on the left, whatever. We could do the right, but it doesn't really matter. Let's choose the left side as our reference side. So xn will be, in this case, 3. So in general, what is my state space in this configuration? What values I can have? Right. Thank you. Thank you, Valeria. Yes, everything from 0 up to n, right? Because I can have 0 molecules. Eventually, I can deplete my left box completely, or I can deplete the right box. So it's anywhere between 0 and n. So that's allowed. All of these states are allowed. And so suppose let's just think about, in the simple case, since you have a visual, what's the probability that if I have 3, that I will end up with 4 uh, balls at the step n+1? So it's missing 1 here. n+1. So it's exactly the picture. It's a little bit not quite 50%. So I think yes, I understand why you're saying 50%, because I said that I'm grabbing uniform at random. But it's not. But it would be 50% if we had 4 and 4. But 3 and 7, yeah, it's 4/7. That's correct. You see the answer in the chat, yes, from Alexei. Right, because I have probability of me grabbing something from the right because I'm grabbing uniformly it's just going to be number of balls on the right, which is 4, divided by the total number of balls of gas molecules, right? So this is in order to increase this number, I need to grab from here. Otherwise, I'm going to decrease, right? And so that's why it's going to be 4/7. What about 2? If I want to go to 2, from 3 to 2. So in this case, I need to grab something from the left, right? So and move it to, sorry, yes, on the left and move it to the right. Yes, 3/7, that's right. And if I want to go from 3 to 5, almost a silly question, but yes, it's 0 because there's no possibility. I can only move one gas molecule at a time. So really, if you think about it, sometimes in Markov chain theory, we write these objects called transition graphs, where I'm going to create a state space, and each element will be a node in this graph. So this is all my possible state space. And so what we're saying here that basically only this can happen. I can go from 1 to 2, or from 1 to 0, from 2 to 1, or from 2 to 3, and so on. So it's kind of a random walk on integers. And notice if I have 0 on the left, then probability of going to 1 is 1, right? Because I will necessarily increase if I have 0 gas molecules in the left box, I'm going to grab from the right with probability 1 because there's nothing else available. Similarly here. So it kind of, as you can see, it pushes you away from the boundary. Like it doesn't like the boundary. It's not a natural state. And so in general, what we just said can be written as following. So if I have, um, I will have n minus I. Sorry, I hope you don't hear my dog is barking a little bit, which it never does. All right, I just checked. Maybe there's a coyote. We have coyotes here, so maybe she saw a coyote, but no. Um, so if I want to go from I to J, and J is I plus 1, that means I am increasing the count, right? So in order to increase the count of my left box, I need to grab from the right. So that means on the right box, I have n minus I. So this is like this n minus I is number of molecules. Oops, what happened here? Or I guess on the right side of the divider, right? And so similarly, if I want to decrease my count, I need to grab the molecule from the left. In this case, I will go to I minus 1, and all the other probabilities are 0. Right, so those are transition probabilities, and which basically defines the system. Yes, I need to decide where to start, and maybe I'll say, okay, I'll start always with 3 molecules on the left, or I can say I'll draw a random number between 0 and n uniformly at random, and that's how we'll start populate the left box and distribute the rest of the balls in the right box. Okay. So this is just an example. It will be useful to us. It will give us some intuition. So, but that's right now how it works. We'll play in the code in a second with it. We're interested in stationary behavior. Like, can we have a system which basically doesn't change much? Like, if you give it this certain configuration, it will sort of stay in this configuration more or less. It will deviate from it, but in a very predictable way, and that's called stationary distribution. And so probability vector pi is called a stationary distribution with respect to a transition probability matrix P if the following equation holds. Oops, sorry, I forgot that I'm doing vectors by like this. If I hit my matrix P on the left with that vector, and so I need to transpose it because it's a column vector, so I need to make it a row vector, I will get pi back. So that's called the global balance equation. As you can see, it's a fixed point equation. It basically means that, applying P, which is a linear transformation, right? It's a stochastic matrix, a transition probability matrix. By the way, in this matrix, rows sum to 1 because of law of total probability, right? So we can make a note maybe where did we define the matrix? Yeah, right here, that you can make a little note that this is a stochastic matrix, which means if I have a vector of ones, I'll get a vector of ones back here. So that just means that the rows of this matrix sum to 1. And matrices like that with positive, well, non-negative entries and rows summing to 1 are called stochastic matrices. So it's a fixed point equation. So if you apply this linear transformation to the vector pi, you're getting pi back. So you're not changing the vector. And so this is called global balance sometimes equations, and it's really difficult to solve for pi or even check this if this holds for a particular pi when your system is really large. Of course, if you have 7 molecules, you have 8 by 8 matrix, P matrix, it's relatively easy, and you can use numerical linear algebra or analytically to do something here. But in practice, this number of states could be infinite, and in this case, it's going to be hopeless most of the time. Okay. It turns out there's an easier condition, but it's stronger condition called detail balance, where we can say, okay, what about the following? What if I require that pi I times pij is equal to pi j pji? So it kind of means that flow between pairs of states, flow in is equal to flow out in some sense. Like the number of molecules that would transfer on average from I to j is equal to the number of molecules would transfer from j to I if we start with the distribution pi. And so that needs to hold for all pairs ij. And that's called detail balance, and that's easier to check than global balance. And the reason I said it is stronger because there's a very simple proposition that says that detailed balance implies global balance. And the proof is really one line, or in my writing here, maybe it will be a couple of lines. But if we start with detailed balance and simply sum over either I or j, it doesn't really matter. So here I'm going to sum over j, pi j pij. So I'm applying this, the summation operation on both sides of the equation. So I have j here, pi j pji. So I didn't do anything interesting yet. I just said let's sum them over j. What happens here is that pi I does not depend on j, so I can factor it out. So pi I is here, summation pij, and then here I cannot factor anything out because everything depends on j, so both terms. But notice what happens. We just talked about it. This is sum of the ith row of my stochastic matrix. It is 1. Again, this is because of law of total probability. If I'm at state I need to go somewhere. So if I sum over all possibilities of where I can go from I, it needs to sum to 1. So this is law of total probability, which basically says that probabilities must sum to 1. Something should happen. And so as a result, we're getting this equation. Pi I is equal to sum over j, pi j e j I. And if you stare at this equation, you'll notice that this is simply, it's writing out this formula right here. So if you use the If you just write out vector by matrix multiplication, that's exactly what you're doing. You're just multiplying matrix P with vector pi on the left, and you're getting your pi back. And so that's why and that's global balance, and that's why we proved what we wanted to prove. The other way around does not work. So it's only one direction. And this chain that the Markov chains that satisfy this property are called the reversible Markov chains. It turns out it's interesting. You can reverse time, and like if you reverse time and go backwards, it's the same probability law applies. You don't have to change anything. Are we okay with that? So far, very, very abstract so far. Let's maybe look at the example. So in the Ehrenfest diffusion model, it turns out. Actually, hold on a second. I want to ask you this. So if you were to guess a stationary distribution of Ehrenfest diffusion, and don't Google or ChatGPT it right now. Let's just play a fair game here. So what do you think will happen if I have, let's say, 100 molecules, lots of molecules? It's a diffusion, right? So with no preference, no drift. So I don't have no preference for left or right. And so if I let it run, what will happen? Like, what do you think will happen with these boxes, with the molecules? They probably will kind of equally distribute each other, right? And so if we think that this will be the kind of the distribution, the stationary distribution of this process, what do you think the mean of the distribution will be? Like on average, if I let the system run, on average, how many particles will I have on the left, X, and number of molecules on the left? Yeah, half of each side. So it will be n over 2. So the mean, stationary mean, it intuitively should be n over 2. What distributions we know that have support between 0 and capital N, like between 0 and some numbers, 0 and 10, 0 and 100? Like what comes to mind? We have seen one of them in this course. Poisson is a little trickier, Yaroslav. Poisson lives on 0 to infinity, right? Poisson can go above N, and we don't want that. Okay, binomial, true. Good. Binomial, that's right. So because binomial is exactly bounded, right? So it starts from 0 and it ends at some number, right? It could be 1 if it's Bernoulli, but usually it's larger than 1. So okay, so suppose I'm like, okay, I don't know any other distributions, which is true actually. I don't know many other distributions with like that with finite support. I want binomial as my candidate. What do you think will be the parameters of the binomial? Remember, binomial has two parameters: the size, got number of Bernoulli trials, and the success probability. So number of trials should be number of molecules, right? Because I want this binomial to be between 0 and n. And so what success probability then I need to have in order to satisfy my symmetrical sort of intuition or intuition about symmetry in the system? A half, right? Because then the mean will be n over 2. And it turns out that's exactly the case. So binomial with this and a half probability of success half is the stationary distribution of this Markov chain. And I will leave it as an exercise. I'll give you a hint of how to do it, but it's very simple. It's very easy to prove. It's not even that tedious to prove that this is a stationary distribution of this Markov chain. Okay, so hold that thought. We will see that in action in the code in a second. Couple of definitions I need to throw at you. I apologize for making it a little bit tedious. A Markov chain is called irreducible if it can get from any state to any other state. So you can go from any state to any other state, but not necessarily always. You just need to do it. I need to be able to do it in a finite number of steps. I don't care how many. Oops, what happens with my pen? Finite number of steps with positive probability. I don't need it to be 1. But if I can do it, that'll be fine. So just a couple of examples for you here. So suppose this is two transition graphs of a Markov chain with 4 states. And so this is another way of basically encoding this transition probability matrix. Instead of writing a matrix, which is not very easy on the eyes when you look at this yourself, it's easy to code. So in the code, we usually keep it as a matrix, but uh, when we draw it like this on the paper, it's easier to think about transition graphs. And so each edge corresponds to one-step transition probability, and it's labeled by that probability. If edge is absent, that means probability is 0. So we don't draw edges with probability 0. So it means that I cannot go from uh, 2 to 1 in one step. But notice I can go from 2 to 1 through 3. First to 3 with probability 1. Actually, I need to go here, and then with probability 0.7 go to 4, and with probability 1 to go to 1. So again, I can go from 2 to 1 in 3 steps, but not in one step. And if I drew it correctly, this should be I should be able to go from anywhere to anywhere in this Markov chain in a finite number of steps. That's why I'm gonna we can call it irreducible. This is an irreducible case. In contrast here, this is not irreducible because I'm getting stuck in some of the subsets. So for example, as when I enter this set, I'm just gonna cycle between 2, 3, 2, 3, 2, 3 deterministically, and that's gonna be very boring and never end. And I will never be able to go from 2 to 4, for example. So that's why this is it's called non-irreducible. What it means is that you can basically reduce it to a smaller number of Markov chains and study them separately because they don't really talk to each other that much. Okay, one more definition, and well, technically two more, the two definitions here. And we're ready to state the main result, which is the only reason and the main reason why Markov chain Monte Carlo works, MCMC works. And so this is our main result, ergodic theorem. But before we go there, just briefly, I want to mention some on finite state space, you don't have to worry about this, but on infinite state spaces, what can happen is that your Markov chain can drift away to sort of infinity and never come back to whenever you started. So we want to prevent this behavior. We want our states to be visited multiple times. And so for that reason, we need this technical term. You can kind of look at it and then blissfully forget about it, to be honest. You don't need it to know that much for practical purposes, but in order to state the theorem, I need to explain what this is. And it's called recurrency. And recurrent means that if you start from any state, you will return to the state eventually with probability 1. It may take you millions of time steps, but you will come back. It turns out that's not sufficient. You also need the random time it takes to return to have a finite expectation. So just think about that. So the time until if I started state 1, like let's say here, and I count in how many steps I will return to it, then this is a random variable because I don't know, like maybe I'll go from 1 to 2, 3, 2, 3, 2 again. I'll get stuck here. Maybe I'll spend here some time and then I'll go here and eventually I'll return. But next time maybe I'll go and I'll come back in 4 steps or 3. 1, 2, 4 in 4 steps. So this is the random variable, and random variables do not have to have finite expectations. Some of them have infinite expectations. Just because the integral or in this case summation or infinite series is diverging, that defines expectation. So for example, Cauchy distribution is a famous distribution which has infinite expectation. So this expectation basically needs to be finite, and that's a condition. Now, the ergodic theorem that says that if you have a Markov chain which is irreducible and is nicely behaved, basically positive recurrent, then what you can do is the following: you have some function, you can keep track. Oops, you can keep track of your steps. So let's say like this: I go and I plug in my state in some function. It could be maybe I'm squaring my states. Maybe I'm just not doing to them anything interesting, and I'm just gonna average. That will converge to my stationary expectation, weighted average, when I'm gonna weight them by my stationary probabilities. So it is really defined as expectation with respect to distribution pi. So this is called time average, and this is called space average. So for example, if let's say f, let me give a simple example. F is indicator function, whether my x is in state 2 or not, right? Then this time average will be this fraction of time. So I visited state 2, and it will converge to the space average, where I will have 0 everywhere. So I'll have 0 times pi 1 plus 1 times pi 2, right? Because of indicator function, plus dot dot dot. So I'll have only white pi 2. So it says that the fraction of time I'm going to visit state 2 is going to give me, in the limit, stationary probability of state 2. How do you feel about that? Positive recurrence and has this effect of people. As soon as I stated the definition of positive recurrence, 2 people left the Zoom. It's not bad, actually. Usually I would expect it 5. Helena is asking about eigenvector. I mean, there's connections. Are you saying pi is an eigenvector of p? That's true. Is it what? Is it left eigenvector corresponding to eigenvalue 1, right? Is that what you're asking? Just because of the definition, pi p is equal pi, so that corresponds to the definition of the eigenvector with eigenvalue 1. So the main notice, like if you look at this ergodic theorem, basically it has the same feel, or actually mathematically the limit looks exactly as the strong law of large numbers. The only difference is that x's are now not independent, right? We are averaging stuff. Empirical averages, which is on the left, give us theoretical averages, which is expectations on the right. So it's actually exactly analogous to the strong law of large numbers, except now x's are not independent. They have this dependence. They have Markov dependence. Let me stop sharing so I can share let's play with the code a little bit. So maybe it will become a little clearer. But first time you see it, it may be a little confusing.
Okay, I typed a question in the chat, but probably you couldn't notice it.
Oh,
I've got
sorry, I didn't notice it. Yeah.
Yeah, so ergodic theorem gives us which convergence? Like almost sure
Oh,
convergence?
yes, sorry, I didn't mention. Yeah, I didn't want to. Yes, it is almost sure convergence.
Yeah,
Hmm.
okay. Thank you. For those who know, it's important for those who
Yeah,
don't
yeah,
know it. Yeah.
right. It is almost sure. So it's in that sense, it's also analogous to strong law of large numbers. So both are almost sure convergences. Yep. Good question. Okay, I think yes, you can see my screen. So this is again little. You have this Sparta file on GitHub already. Um, sorry, my annoying AI assistant is trying to give me some code completions. Uh, so let's play with this infinite diffusion. So what I have here, I have a little function with kind of Roxygen documentation specifying what each parameter means. So I have function which takes two parameters: my current state, so number of molecules in the left box, and the number of molecules, right? So that was in the picture I drew before. It was 3 and 7, and it gives me either it doesn't do any checks whether I can plug in something silly here like a negative number, which I didn't check here if I do it or not. So I'm assuming the inputs are correct. And then what I'm doing, I'm basically flipping a biased coin with a probability equal to this. And the way to flip a biased coin, the easiest way to flip a biased coin is to generate a uniform distribution and check whether you have that uniform distribution will be on the left of P or on the right of P. That just by definition of uniform distribution, you will get a biased coin back. If you haven't seen that trick, think about it. It's not anything complicated, but it's just maybe unusual if you see it for the first time. But this is basically flipping a biased coin with probability equal to I over n. That's how we wrote it in the lecture a couple of minutes ago. And in that case, I go down, else I go up. That's all, right? So um, if I run this chunk of code, it just defines a function. Then the next chunk of code, I'm going to set up the system. I'm going to have 100 molecules. This will be my number of iterations, number of time steps. I'm going to evolve my Markov chain, 1,000. We'll increase it in a second. And then we will initialize a chain. I'm going to allocate space by allocating a numeric vector of size 1,000. So just I have it. And then I'm going to put in the first element, I'm going to just put a random sample of numbers between 0 and n. I'm just going to draw a number and then say, okay, this is my initial configuration. So if we do that, for example, if you look at my draws, um, let's see. This is a vector with all the zeros, except the first element will be some random number. It actually ended up being 89. So this is my initial system, right? I initialize my distribution. And then in the next one, it's a simple for loop, which I'm going to evolve. Given my previous draw, I'm going to stick it into my next state function that I wrote, and I'm going to give it number of molecules. So, right? So it's going to go to 89, produce some random number here, and then grab that number, produce something else, and then in the for loop, it will evolve this. So if we do that, and now this filled it with random numbers. So now I have these 1,000 random numbers that came from this Markov chain. Let's visualize it so that it's easier to look at. So this is our path. So we started 89 and using this simple rules, that's the number of molecules bounces around. And as we kind of predicted, it likes symmetry. So it kind of goes to 50 and starts oscillating around 50 because that's the 50-50 configuration of the system, right? And now remember, theoretically, the ergodic theorem, remember, now let's think about what ergodic theorem says, that if I average this path, that should give me 50 because that's my empirical average across time should be equal to stationary mean. If I take, let's say, sample variance of this path, it should be sample variance of the binomial distribution of the stationary distribution. So let's do that. So here, this is the mean of my draws. This is the variance, sample variance of my draw. So this is just sample path. This is theoretical, right? This is my binomial mean is n over 2. Binomial variance is n times p times 1 minus p. So that's n times 0.5 times 0.5. So this is n over times 0.25 or n over 2. Sorry, n over 4. I didn't have my coffee yet. So this is what happens. It's 52 here. The variance is 58, so not correct. And but the mean is pretty close. And we are wondering if now our math has failed us. Not really, because we didn't have enough iterations. So if we repeat that with 10,000 iterations now, so the same process. So this is our Markov chain now. So notice it looks much more stationary, so to speak. It looks like white noise, which is what stationarity should look like. And then if we go and take this time averages, now we're much closer. It's still not perfect. It's 26, whatever, but it will have always some, sampling variance. So basically what we learned, notice that we could do math and find out the station distribution, and you will do it in the homework. You will prove that binomial is a station distribution, or we can just simulate the hell out of it, right? Just simulate an average, and this will give us properties of the station distribution. If you plot the histogram of this, which I forgot to do, I should add that actually later. I don't want to do it on the fly. It will look like binomial. Very close to binomial, the histogram of that sample. So we basically can get all the properties of stationary distribution just by running a Markov chain forward. If we know that it has a stationary distribution, but we don't know what exactly it is, we can study properties of the stationary distribution by simulation instead of doing analytical formulas and torture ourselves with some algebra. And that's the key insight here in terms of MCMC as well. Any questions about this?
Is it just a coincidence that the mean converged only after, I think, 100 trials, while the variance needed much, much more trials to start to be close to the true value?
Not a coincidence. It's a good question, Valeria. Yes, mean is always easier to estimate than the variance. It has to do with Monte Carlo error. So basically, all of the quantities we're estimating, and that's something I didn't have to talk about even in Monte Carlo, unfortunately. It's not even Markov chain specific. It's for Monte Carlo as well. Whatever you're trying to approximate using Monte Carlo, Markov chain or non-Markov chain doesn't matter. Your Monte Carlo error will be different depending on what you're trying to approximate. And basically, Monte Carlo error of variance is higher than mean always. So variances or quantiles are harder to estimate always than the mean. Mean is the easiest. Okay, so let me switch real quick to lectures, but then hopefully we'll have time to jump back to the code. Okay, so we just saw the ergodic theorem in action. I hope you that you connected that. That's exactly what we just did, right? So we used this formula. So when we took an average, a sample mean of the Ehrenfest diffusion, we got back our stationary mean of the binomial distribution. So that's exactly what happened in the code. So okay, Markov chain Monte Carlo. The big idea is brilliant, but if you think about it, it seems a little too easy. But it's completely backwards from how we think about Markov chain theory from a mathematical point of view. So if you take a stochastic processes class anywhere in the world, you will be given a Markov chain and you will be asked to study it and find its stationary distribution if it exists or something else and so on. Here, we're going to flip it. We're going to say, suppose I have a distribution that I need to study. Can I artificially construct a Markov chain with a stationary distribution that is my object of my desire? Do you see that it's completely backwards, right? So we're gonna start with this distribution. In our case, this will be our posterior distribution in Bayesian inference, but it could be anything. In statistical mechanics, people study, lots of other distributions of energy, distribution of molecule configurations, and so on. So it can be anything you want. And we're going to artificially design or engineer a Markov chain that will converge to that stationary distribution. Because then we can just evolve this Markov chain, simulate the same way we did this just a second ago in the code with Ehrenfest diffusion, and we can study and get at the properties of the stationary distribution via simulation. So it took people about 50 years to get to that idea, and it took statisticians another 30 years to wake up to this idea. But eventually we got there. And so it means that if I want to study my Bayesian posterior distribution, I can design a Markov chain that will converge to it completely artificially. And this is the way to do it. Actually, it's called, I don't want to confuse you. So if you look up at the other literature, you will see that this is called Metropolis Hastings most of the time. Algorithm. I refused to call it Metropolis Hastings because Metropolis actually didn't do anything. It was Rosenbluth, Ariana Rosenbluth, who developed the code and did most of the work. But at that time, the convention was that the head of the physics lab was the first author. So the first author of the manuscript is Metropolis. It's a 1953 manuscript. But Ariana Rosenbluth is the real hero here, not Nick Metropolis. So the objective here is to estimate some expectation. So it's very generic, but in our case, it will be posterior expectation or posterior variance or posterior quantiles. It's a little difficult with quantiles because they're not quite expectations, they're solutions to integral equations, but trust me, it works the same way. It's just you need to do one more step there. So we have a target distribution. Let's see if so in Bayesian inference, this target distribution will be our posterior. Notice that I'm making this point here that the normalizing constant does not have to be known. So I don't need to know my normalizing constant of my posterior in order to run this. That will be important. Actually, it's critical. If that was not the case, this would be the most useless algorithm in the world. But it's not. But we don't know. We don't need to know the normalizing constant. And so the way it works is we're going to simulate, we're going to start at any value, and then we're going to simulate some proposal distribution or value from a proposal distribution. So we need some proposal distribution, which given my current value of my Markov chain, let's say I, gives me next state. So, but it's only proposal. I'm not going to accept it yet. So I'm proposing, and that proposal could be anything. This Q is very arbitrary. There's some constraints on it, but almost anything reasonable will work. As long as it will produce irreducible Markov chain, actually it will work. So irreducibility is the only constraint here. And then we're going to compute acceptance probability. Which called Aij, which is going to be a minimum between pi j q I given j, pi I q j given I. It's kind of weird symmetry here, and 1. So the reason it's minimum between this and 1 is just because we want it to be a probability. So if it's above 1, we're going to bound it and say if it's above 1, then accept with probability 1. If it's below 1, then we're going to do this biased coin trick that we just have seen, right? We're going to draw a uniform distribution between 0 and 1, and we're going to accept y is equal to j with probability Aij. Which means that really my next state of my Markov chain will be j, or whatever y, y is a conceptual random variable, j is the actual value that we produced. If that uniform distribution will be less or equal than Aij, and I, then that's our xn, the state that we had before, if U is above Aij. And if it's above 1, that's fine too. Like if Aij is above 1, for example, then U will be less of it, and we automatically accept. So this formula right now works, and you don't have to take any minima of anything. But formally, we're doing that. Right? So we are proposing and then accepting, rejecting, proposing, accepting, rejecting, and that defines our Markov chain. And it turns out, and notice, if I don't know the normalizing constant, suppose I didn't know that, oh my God, I have 1 over C here and 1 over C here, it canceled out. It doesn't matter. Right? So if I don't know my normalizing constant, if I know my station, my pi only up to normalizing constant, I can still use this because pi comes into the equation only as a ratio. So normalizing constants will cancel out. Okay, you will actually prove in the homework. It's very easy to prove that this has the desired stationary distribution. And the hint that I'm going to give you right now, and I probably will repeat it in the homework as well, is that transition probabilities of this Markov chain are Pij is, if I want to go from I to j, first I need to propose it. And then independently, I need to accept it or reject it. So it's a product of my proposal probabilities and acceptance probabilities. So given this Pij, it's very easy to prove that detailed balance holds. And if detailed balance holds, that means the global balance holds and pi will be a stationary distribution. Okay, I have computer demo just for a second, so I have only 2 minutes, but let me, it's a short demo though, so I will have a little bit of time. Okay. Okay, so here's this demonstration. So suppose I wanted to sample from a standard normal distribution, and suppose I didn't, suppose I didn't know how to do it, which is silly. I know how to sample from a standard normal distribution, but it's an exercise, right? So then what I could do, it for some reason doesn't render in our studio. Um, Sorry, let me switch real quickly to. It renders in my in Visual Studio, I think. Yes, it does. Okay. So I have my standard normal distribution, and so in order to generate this Markov chain, what I could do, I could first generate a uniform proposal. So what I'm going to do, I'm going to say, suppose this is my current value, xt, in the formula, and I'm going to perturb it by uniform distribution centered at 0. So I'm going to do a little bit of perturbation, uniform perturbation of my current state, and then I'm going to accept, reject it according to this, our rules of that we just defined. So my next state will be either perturbed current state or the current state. And notice that in the acceptance ratio that I worked out, and you can check with this algebra for yourself, the normalizing constant 1 over 2 pi, that annoying bit, is absent because it canceled out. So even if I didn't know how to normalize normal distribution, I just knew it, oh, it's proportional to e to the negative x squared over 2, but I don't know, somehow normalize it. I don't know how to do it. It wouldn't matter, which is important because in Bayesian inference, we never know the normalizing constant because it's that high dimensional integral that we don't want to take, right? And so in this code, what I'm doing, I'm just basically implementing this formula, right? So I'm drawing a uniform distribution, realization, and this tuning parameter negative delta just tells me how far do I go, how far I perturb my current value. And then I accept reject it using this statement right here, using a biased coin. And let's try to do it, and I'm just running a for loop. So if you do it for certain delta, you'll get this, which looks disappointing, right? So notice I started at 5. It's really far from where normal distribution should be. Normal distribution is centered at 0, and plus minus 2 covers most of the values. So 5 is a crazy value for normal distributions, for standard normal distribution. So that's why it doesn't like it. It goes down and it eventually finds 0. But this looks like nowhere like normal distribution because my convergence is very slow. So it took me a long time to get to stationarity, and I'm not quite there yet. And that's because when in this code, what I did, I used my, when I ran it, my tuning parameter was very small, 0.05. So I was perturbing my current value, let's say 5, by saying, okay, maybe add 0.02, 0.03, or subtract 0.02, 0.03. So it's very small steps. So now what we're gonna do, we're gonna change that and use the value, where is it? Large jumps right here. I'm going to value 5. So those are huge jumps. So I'm going to do plus minus uniform distribution distributed between -5 and 5. Sometimes they're crazy, so I will be rejecting a lot. But these large jumps produce this chain right here. So both chains are correct. Both chains theoretically work, but this converges much faster. And notice it looks like what's called in MCMC business, it's an official term, believe it or not, it's called fuzzy caterpillar. That, it looks like a caterpillar that is trying to crawl, I don't know, in someone's nightmares maybe, but whatever. But on the right, you have a histogram which looks pretty close to normal distribution, standard normal distribution. And if you take, mean and variance and so on, you'll get 0 and 1 and so on. So it will work. So ergodic theorem works here. But the key here is not that the ergodic theorem works, that we artificially constructed the Markov chain ourselves. Like it was not given to us. We did this artificially in order to be able to simulate from it and get to the distribution we want, which is standard normal. Which is very much backwards from how a mathematician would think about stochastic processes, where you are given a stochastic process and you want to study it. Here you are given a distribution that you want to study, and you're constructing a stochastic process artificially in order to simulate that stochastic process and get to the properties of the distribution you want. So it's a very key difference. All right, now I am officially ended.